Quantum entanglement is a physical phenomenon which occurs when pairs or groups of particles are generated, interact, or share spatial proximity in ways such that the quantum state of each particle cannot be described independently of the state of the others. Even when the particles are separated by a large distance, instead, a quantum state must be described for the system as a whole. Measurements of physical properties such as position, momentum, spin, and polarization performed on entangled particles are found to be correlated. For example, if a pair of particles is generated in such a way that their total spin is known to be zero, and one particle is found to have clockwise spin on a certain axis, the spin of the other particle, measured on the same axis, will be found to be counterclockwise, as is to be expected due to their entanglement. However, this behavior gives rise to seemingly paradoxical effects. Any measurement of a property of a particle performs an irreversible collapse on that particle and will change the original quantum state. In the case of entangled particles, such a measurement will be on the entangled system as a whole. Given that the statistics of these measurements cannot be replicated by models in which each particle has its own state independent of the other, it appears that one particle of an entangled pair knows what measurement has been performed on the other, and with what outcome, even though there is no known means for such information to be communicated between the particles, which at the time of measurement may be separated by arbitrarily large distances. Such phenomena were the subject of a 1935 paper by Albert Einstein, Boris Podolsky, and Nathan Rosen, and several papers by Erwin Schrödinger shortly thereafter describing what came to be known as the EPR paradox. Let's take a closer look at this seeming paradox. The essence of the paradox is that particles can interact in such a way that it is possible to measure both their position and their momentum more accurately than Heisenberg's uncertainty principle allows. Unless measuring one particle instantaneously affects the other to prevent this accuracy, which would involve information being transmitted faster than light, is forbidden by the theory of relativity, or what Einstein called spooky action at a distance. This consequence had not previously been noticed and seemed unreasonable at the time. The phenomenon involved is now known as quantum entanglement. Per EPR, the paradox demonstrated that quantum theory was incomplete and needed to be extended with hidden variables. One modern resolution is as follows: for two entangled particles created at once, e.g. an electron-positron pair from a photon, measurable properties have well-defined meaning only for the ensemble system. Properties of constituent subsystems, e.g. the individual electron or positron, considered individually, remain undefined. Therefore, if analogous measurements are performed on the two entangled subsystems, there will always be a correlation between the outcomes and a well-defined global outcome for the ensemble. However, the outcomes for each subsystem, considered separately, at each repetition of the experiment will not be well defined or predictable. This correlation does not imply that measurements performed on one particle influence measurements on the other. This modern resolution eliminates the need for hidden variables, action at a distance, or other schemes introduced over time, in order to explain the phenomenon. In November 2016, researchers performed Bell test experiments in which further loopholes were closed. The Bell test experiment is a real-world physics experiment designed to test the theory of quantum mechanics in relation to two other concepts, the principle of locality and Einstein's concept of local realism. The experiments test whether or not the real world satisfies local realism, which requires the presence of some additional local variables called hidden, because they are not a feature of quantum theory to explain the behavior of particles like photons and electrons. According to Bell's theorem, if nature actually operates in accord with any theory of local hidden variables, then the results of a Bell test will be constrained in a particular quantifiable way. If a Bell test is performed in a laboratory and the results are not thus constrained, then they are inconsistent with the hypothesis that local hidden variables exist. Such results would support the position that there is no way to explain the phenomena of quantum mechanics in terms of a more fundamental description of nature that is more in line with the rules of classical physics. Many types of Bell tests have been performed in physics laboratories, often with the goal of ameliorating problems of experimental design or setup that could in principle affect the validity of the findings of earlier Bell tests. This is known as closing loopholes in Bell test experiments. In a novel experiment conducted in 2016, over 100,000 volunteers participated in an online video game that used human choices to produce the data for researchers conducting multiple independent tests across the globe. To date, this and all prior Bell tests have found that the hypothesis of local hidden variables is inconsistent with the way that physical systems behave. The Big Bell test asked human volunteers, known as Bellsters, to choose the measurements in order to close the so-called freedom of choice loophole, the possibility that the particles themselves influence the choice of measurement. Such influence, if it existed, would invalidate the test. It would be like allowing students to write their own exam questions. This loophole cannot be closed by choosing with dice or random number generators because there is always the possibility that these physical systems are coordinated with the entangled particles. Human choices introduce the element of free will by which people can choose independently of whatever the particles might be doing. Led by ICFO, the Institute of Photonic Sciences, in Barcelona, the Big Bell test recruited participants worldwide to contribute unpredictable sequences of zeros and ones bits through an online video game. The bits were routed to state-of-the-art experiments in Brisbane, Shanghai, Vienna, Rome, Munich, Zurich, Nice, Barcelona, Buenos Aires, Concepcion, Chile, and Boulder, Colorado, where they were used to set the angles of polarizers and other laboratory elements to determine how entangled particles were measured. Participants contributed with more than 90 million bits, making possible a strong test of local realism, as well as other experiments on realism in quantum mechanics. The obtained results strongly disagree with Einstein's worldview, closed the freedom of choice loophole for the first time, and demonstrate several new methods in the study of entanglement and local realism. It just keeps getting weirder. Thank you, and as always, thanks for watching. Please like if you like and don't forget to subscribe and ring the bell for new content. Aurelius V2V Podcast.